Parce que, ouais, avec le micro, il marche. Le petit bouton vert qui s'allume. Ok, ouais. Bon, ben nickel. Okay, so hello everyone. Let's start again. So today it will be about. So today the content will be about quantum entropy and the relationship between the quantum entropy to compute entropies of reduced density matrix, but not with respect to particles, but with respect to orbitals. So that's the first thing that I will introduce. And so why is it useful? It's useful for, well, two, let's say results. So the first one will be a theoretical one, which is about why DMRG works. So why DMRG works for one-dimensional nearest neighbor interaction Hamiltonians. So this is related to the area law. And also about how to make DMRG work, because you have seen that, so there was this little example that I presented to show that the representability of the state was sensitive to the ordering. So how to pick a good ordering a priori is not obvious if you just look at the wave function. And so there are tools using mutual information that are used to kind of have a proxy for to guess the good ordering. And so this mutual information relies on the computation of quantum entropies of some reduced density matrix. So let's go. So quantum entropy. Yeah, I think it's a 4. Yeah, I don't know. So quantum entropy. And first, so reduced density matrix. So here, yeah, I will have a state. So I will have a state that will be represented by this tensor here. So I have L sites. So yeah, from now on, the orbitals will be sites. So I think I will use this word a bit more often. So what I mean site is just the collection of, well, it's just the labels from 1 to L. Okay, so the sites, it will be just 1, 2, and so on until L. Okay. Yeah, it's the same object. Yeah. Just to emphasize that it will be a reduced density matrix associated to a quantum state. I mean, I think previously I should have used psi also, but yeah. Yeah. So the usual. So the reduced density matrix that you all know is just this one. So the many-body reduced density matrix. And so to define a reduced density matrix on just some subset of these sites, so would be the following. So so here this you can view it. Then you can view it as a big matrix. Maybe I should start with this, which have these indices. So probably I should put a star here if these are complex. Yeah. Okay. And so this is for all mu and mu. Yes. Yeah. So it's a big. So this one is a big matrix. And now, if I want to define reduced density matrix, which is associated to some of the sites. So A will be a subset of the sites. Then I define rho of A being, so yeah, I will write different formulas, okay? So it will be the partial trace when I don't take the indices in A, okay? So which usually it's written like this, for example. So side side. And so the dimension of this partial this reduced density matrix, it will be R to the 2 times yeah, the cardinality of A. Yeah, where this is yeah, this is the cardinality of A. To write it yeah, so if I want to write it yeah, the formula, so it would be so rho of A, and this is mu A, it will be then the sum over all the indices that belong to B of yeah, of C mu A mu B psi mu A mu B. Okay, so it's the exact same formula. Yes. Over all the indices that are not in A. So it's A that you cross. So it's not in A. Yeah, well, okay. I put an arrow, just remove the arrow if you want. It's A bar, if you want. A data cross. I don't know. Yeah, then it will be the trace over B. Yeah, or the other way to write it if you want. Yeah, it's writing 1L as A union B with the disjoint, well, with the void intersection, and then rho A will be the trace over B of psi psi. It's the A, yeah. Yeah, over the complementarity set of indices, and this is kind of depicted in the formula here. You fix the indices that belong to A, and you sum over the indices that belong to the complementary set.
I guess there is no easy link with the density matrices with respect to particles.
Yes, there is, because, for example, the one site RDM, it will be it will be the one site RDM is exactly the representation in the basis, in the computational basis of your one electron RDM. I think so. Well, you can reconstruct from it, maybe. Yeah. Yes, yes. So yeah. So it's here. Yeah, it's a subset of sites, and then I'm computing a reduced density matrix with respect to these sites. I think there is, because, for example, so if you take rho I, then it's the trace, well, for psi, but for yeah, well, not I, and here these entries, you see it can so if psi preserves the number of particles, then basically you have so it's a 2 by 2 matrix. it's a 2x2 matrix, mu I, which is, yeah, so 0, 1, 0, 1. So these are the labeling. And so since it preserves the number of particles, it has just, it has entry 0 of diagonal. And for this entry, you get it by looking at, yeah, so it will be AI. So I destroy and I create. So this will be this entry then.
You have access to the diagonal element, but not to the.
Ah, yeah, to the, okay, yeah, okay, yeah. Okay.
But if you write the I dagger I J.
No, but maybe you can get it from the two. No, okay. Well. Yeah, okay, okay. Okay, you can have access to some elements, but not everyone. Okay. Yes. No, 0, 0. It's because then you would, because this term is when you trace. So this is associated when you trace with respect to everything that is. Yeah, 0 means that you have no electron. And so if you have n electron, you have traced over states that have n electrons. And so, yeah, you have traced, over states that have n electrons. Okay, so the same number here. Whereas here you would have, would have to have different numbers of electrons, like, in your state on the left and on the right, you see. Well, yeah, it's a bad explanation, but yeah. Okay. Yes, okay, you have access to the data elements. Okay. So maybe just a few properties. First, the thing is this reduced density matrices, they have trace 1 or property. So the trace of this row A is equal to 1. And so this is so the proof is kind of it's because the trace of row A. I mean, okay, it's because then this trace, it's in fact a trace over the elements that belong to A. And here it's if you are doing the trace of A and trace, so I'm using the notations over here of psi psi. So this is just then the trace over all the indices. So it's the trace of the A unionly. And so the trace over over the normalized state is U1. So this is something, yeah. And the other thing that is interesting is to take a particular example of a set A. So yeah, in what follows, what I will use are A that are one site RDM, sometimes two sites, so for the mutual information. And otherwise, it will be the first K sites. So for the first K sites, then one, so this thing here, it will be then, so if I use the formula over here, it will be a bit, so it will be the sum over mu K plus 1 to mu L. Okay, here I'm just writing all the indices just to, yeah, no, it's new, it's not new. Hop. You trace over these. And so the thing is, it's interesting to view it as, so then what you see is that this is nothing but the matrix product between this one. Okay, so if I promote this to a matrix, it's just this then. And so, yeah, so I will write it this way. Okay. So now it's really a matrix multiplication where this has size 2 to the k times 2 to the L minus k. So here it's R2 L minus k times 2 to the k. And you see it's the reshape times its transpose. Okay. I mean, I just get this one by flipping the row and column index. So what we can write is, for example, the SVD of this guy. And if you write the SVD here, since it's the matrix times its transpose, what you obtain is U sigma, well, sigma transpose U transpose. And so the eigenvalues of the reduced density matrix are nothing but the singular values of this reshape. So why it is interesting? It's interesting because these singular values, they are exactly the ones that are dictating the approximability by tensor trains. So if you remember in the TT approximability result, I will recall the norm of some tensor by its, yeah, this looks like pi. This was smaller than a sum of the sigma, yeah, let's call it. Okay. So if I select a bond dimension, so this, yeah, put squares everywhere. And these sigma jk, they are related to so these are the singular values of the reshape here. Okay. So looking at the singular values of this guy, so and it's a sum of a k also. Okay. So looking at the singular values of this guy for all k is the same thing as looking at the eigenvalues of these reduced density matrices for all k. So you, yeah, so since it's equivalent, I mean, this is yeah, this is kind of the picture that so this is yeah, the object that we are going to consider. And now, so now the thing is, what you want to have a good approximability by tensor trains is to have this to decay fast. Okay, so you want the singular values to decay fast. So you want the eigenvalues of your matrix here to decay fast. So now you want, so, and of course you don't want to build this object. It's just you want some kind of a proxy that is giving you what is the nature of well, what is the behavior of these singular values. So that's kind of to me the meaning of the quantum entropy. So it gives you kind of a metric of the decay of the eigenvalues of your reduced density matrix. So to me, the entropy, yeah, well, I will kind of a metric of the decay of the eigenvalues of your reduced density matrix. And so what do you want to have for this metric? So let's call it, so the entropy, I will call it S. So you have, what do you mean for all R's? It's a K. So for a fixed K, you want a metric of the decay of the singular values of your density reduced matrix. Yes, you have an entropy for each K, yeah. And so let's kind of make a wish list. So yeah, I mean, okay. So maybe this I will replace by A, which is a subset of indices. Okay, A is just a subset of the indices. So let's make a wish list of what we want for our metric. First, we want if this describes a pure state. A pure state is what? Is just if this matrix is of rank 1, we want the entropy to be exactly equal to 0. Okay. So rho of A is of rank 1. This should be equivalent to S of rho A is equal to 0. So yeah, and since it's a metric, yeah, maybe a 0 condition is that the metric should be non-negative. Okay, since it's a metric. So the 0 condition, and you want to have this. So if rho A is of rank 1, so since this object has yeah, and something that I haven't said, but yeah, I mean it's kind of clear if you look at this. This is symmetric. Okay, the reduced density matrices, these are symmetric. So yeah, you can list it here. So rho A is symmetric, or Hermitian if it's if you have it's symmetric, and the other thing that you can kind of view here, it's symmetric and it's non-negative. So it's so in this case, when rho A is of rank 1, the eigenvalues they are exactly 1, 0, 0, 0. Okay, so then the eigenvalues it's 1, 0, and so on. Okay, so now another property that you want to have is that if the reduced density matrix, so if your density matrix is in fact a product, okay? So if you're looking at the tensor product of two density matrices, meaning that A and B are not correlated, this is a product state, then you want to have that the entropy of the product state to be the sum of the entropies of the single RDMs. So this property is called additivity. Okay. So this will be defined on all the rows. So on the rows that you can build. Okay, yeah, that's true. Okay, so related to your question, yeah, the S will be defined for all the row A's that you can build. Yeah. So that you will have the same definition then, because it will just be intrinsic to the matrix. I mean, if you know the von Neumann entropy, it will be the von Neumann entropy. But I will speak about the Renyi also. Okay. Okay, so additivity. Now, something that you can wish also is that now you're looking at the density matrix over A and B, okay? Over the union of sites A and B. And you want to compare it to the density matrix, so the entropy of the density matrix over A and the one over B. So here what you have is that you have internal correlations that are between A and B. that you don't see. Whereas here, basically by locating I'm not sure it's the right word, but yeah, by localizing this reduced matrices, this RDM to A, you see the correlation between A and B. And so since this should be a measure of the complexity, so the thing is correlation will be seen in the decay of the singular values, of the eigenvalues, sorry. So if the eigenvalues decay slowly, it will mean that you have a lot of correlation that is happening between your set of chosen indices and the rest of the system. And so here, since you have internal correlation that you don't see here, what you want to have is that if you sum these entropies, you want this to be an upper bound of the entropy of the union of the both systems. So this property, it's called the subadditivity. Okay. And finally, something that is maybe maybe fancier. So yeah, I will give the name after. Is that if you have a partition, well, if you have three partitions of your system, okay. So you have A, B, and C, and you want to compare to if you want to compare to the entropy of A and B and C. So here, since you are accounting for the possible correlations between you see here you are accounting for the correlation between AB and the rest of the system, and here BC with the rest of the system, but which is involving B. So you would like to say, well, I am accounting for an extra correlation that I have in B. So you want to kind of remove this contribution. And so here, since you are not describing internal correlations, you want this inequality, okay? So this is the strong subadditivity. Okay. So that's kind of the wish list that you want. And if you have this, you believe that, if everything is satisfied, you believe that then S is small if it's close to a pure state. So it means that you have strong decay of the singular values. And if you have a strong decay of the singular values, then it should reflect the fact that it's approximable by tensor trains. Otherwise, it's not. Okay. So that's kind of what you want. And so let's see an example of, so now it will be the von Neumann and the Rényi entropies. Okay. So I will give two definitions of two different entropies, and let's see if it satisfies our wish list.
What I understand is that if you have correlation between A and B,
yes,
therefore you have more orders and then less entropy. That's what it means.
Yes, because these are internal correlations. Whereas here, okay, here this is a proxy of the interaction of A with the rest. Okay, this as the entropy of row A. what I call a proxy is it's a number that tells you how much correlation you have between A and the rest of the system. And same thing for B, okay? And since here you can have correlation between A and B that you don't see here, therefore, this quantity should be smaller than this one.
Then say that S of rho AB don't measure the correlation between A and B.
No.
That's counterintuitive.
Yeah, it's AB is just yeah the where it acts. Yeah, I don't know.
Measure the correlation of the subsystem with the rest.
Yes. Yeah. Okay. Yeah, it's intrication. Yeah, entanglement. Yeah, it's entanglement. Yeah, yeah, it's entanglement. Yeah, I should say entanglement. In fact.
Rho AB does not measure the entanglement between A and B.
No, because it's internal entanglement that you don't see.
Okay.
I mean, it's like when you look at the whole. I mean, okay, I'm not saying it's very convincing, but I mean, if you take all the sites, okay, from 1 to L, well, then you don't trace against anything. And this is a pure state. Because you don't see any internal correlation, internal entanglement. Yeah, you just have side-side. Yeah. Now, once you start tracing out some sites, then you see the entanglement between the sites that you have kept against the one that.
So the complexity of your site tells you how far you are from a pure state.
Yes.
And the pure state, it can be like site can be super correlated in equal way. You don't care. It's not the road is not giving you any information on the amount of strong correlation that you have inside. About the entanglement.
Okay, yeah, okay. So from now on, I should use entanglement and not correlation. Yeah. Okay. Yes.
You mean by pure state?
Pure state is a rank 1. Okay. So let's look at two examples. So namely, so these are the examples that are standard when you are looking at well on the entropy of reduced density matrices. So you have the von Neumann entropy, so which is defined by this. And you have the Renyi entropy, so which depends on the parameter alpha, which is given by this, I believe. Yes. So yeah, how do you compute these quantities? I mean, these quantities, if you diagonalize rho, so you write rho equal to u to q lambda q transpose, where lambda is just lambda 1 that. Then yeah, the first formula is just minus the sum of lambda I log lambda I, and the second one is just 1 minus alpha log of the sum of the lambda I to the power alpha. Okay. Yeah, and the alpha I should say, so it's positive and different than 1. Okay. Okay. Yeah. Yeah. I guess so. I mean, well, yeah. I mean, I work anyway in this Fokker representation picture, so yeah. Okay. Just a second. Ah, yeah. Okay. So that's what we are going to find out, and yeah, let's not go to, yeah. I realized that I have not printed the right notes. Just a second. So yeah. There are things that I should have printed that I didn't print. So yeah, maybe one thing that can be interesting is to yeah, maybe to look at first at some example. So just to compute. So as you see, I mean, so for example, we just compute one of these entropies. So then the entropy is just a quantity that depends on the eigenvalues of your reduced density matrix. So let's see that we take the worst case in terms of decay. So let's assume that we have. So we are looking at this reduced density matrix, and we assume that. So we suppose. Yeah. So suppose that. That this reduced density matrix has eigenvalues. So we will suppose that they are all equal. So since this object is of size 2 to the k times 2 to the k, and the trace is equal to 1, then if they are all equal, the eigenvalues are all equal to 1 over 2 to the power k. And so let's just compute the fundamental entropy of this thing. So I have a sum 1 to the power k. So from 1 to the 2 power k of the log of 2 to the power k. So usually the log here is the log in base 2. I mean, it doesn't really matter, but here it's convenient. So here, since you have summing 2 to the power k times the same term, so this factors goes out and you just retrieve k. And so here, what is interesting is that you see that the entropy scales linearly in the number of sites. Okay, so so this remark is kind of, so the k that you have here is the same here. Maybe a second example that we can do. So that's what we are going to see. Maybe something that is also interesting is to look at the case where rho is, for example, calculated from a state that you have described using a tensor train. Okay, so yeah, this was my first example. Second example. So let's say that rho is computed from psi given by a tensor train. So in that case, if you have a tensor train of rank R, so in that case, if you look here, then since you have a tensor train of rank R, if you look at the reshape of your state, you have at most R positive singular values, and the rest is 0. In that case, rho of, yeah. has at most R positive eigenvalues. So this is because the eigenvalues, they are the square of the singular values of the reshape, and this reshape is related to the approximability of your state. And so let's look again at the worst case when they are all equal. Okay, and so suppose they are all equal. Then the von Neumann entropy in this case, it's minus, so the sum. So if they are all equal and you have R positive, then they are all equal to 1 over R. Okay. And so you have summing over, yeah, so here the sum. So here implicitly, you say that 0 times log of 0 is 0. Okay. So you just have this then. Okay. Yeah, and so here you are summing from 1 to R. So this 1 over R goes out, and so you have a log 2 times R. So the rank in the exact case, the TT rank, it can only, so it goes at most exponentially. So in the exact case, when R depends exponentially on the size of your system, then you retrieve well, you have the same scaling here. But if you kind of fix the tensor train rank, you see that you are limited, and you, let's say that you increase the system size. So let's say you are looking at L that is bigger and bigger, and you fix R, then you see that basically you cannot retrieve states that are like this. Okay, because simply this scales as the system size, whereas here this is fixed by the description that you have. Okay, and so this kind of tells you, in a way, that you have a nearsightedness in the tensor train representation. So it's, well, to me, it reflects the fact that you have a nearsightedness in the tensor train representation of your state, that you cannot encode states that have entropies that are, that are too large. Yes.
Can I ask you a favor?
Explain again.
Like just write the density matrices, that definition, with the state that you gave us before. You know, like
the one example that I gave. Yeah. Yeah, but it's cumbersome. But they are in the notes, so there will be notes, and it's derived, so you can yeah. So it's derived for one site and two sites, but yeah.
So it's the point that you single the monument for the many problem, but since it's entangled.
It's entangled because you are in the wrong basis, basically. Yes. But I will come to that later. Yeah, it's tied to the choice of the basis. Yes. So if you change the basis, you can have different entropies. But it's yeah.
don't mean the order.
No, I don't mean the order. I mean the sites here. If you change the nature of the sites, which are basically the orbitals that yes. Yeah. The thing is, yeah. I mean, this is more, yeah, because this is more developed for systems with translational invariance and really like spins. Yeah, so for spin systems. So that's why.
If you use a set of particle orbitals or a set of MCSL orbitals, you don't measure the same entropy.
Yes, exactly. Yeah.
So the entropy, if you measure in the set of AU, for instance, the entropy of the particle ground state will be more zero.
Yes. Yes, it won't be. Yes, because it will be a pure state in the MO basis, but not in the AO basis.
So therefore, if you have a correlated state, like a multi-configuration, like to take the full CI in the article basis for like some weekly correlated system like again or something, what would you measure as an input? It's going to be low. It's close to half a clock, but not.
Well, then it will be low if it's. I mean, yeah, it should be, yeah. Maybe I misunderstood your question, but
Like,
if it's
the compactness tension within the basis.
kind of should measure that, but yeah. Yeah. Okay. So now basically what I think I will discuss about until the break is well, what can we say about these two notions of entropies, and do they satisfy the wish list criterion that I've given there? So let's see. So for the first two, in fact, what I will introduce. So yeah, these two notions, they can be summarized in one proposition by stating that the entropy are Schur concave. I will explain what Schur concave means. It's the same Schur than. No, it's not this. Oh, okay. I don't know. So proposition. So this one and this one are Schur concave. So what does it mean? Schur concave. So Schur concave. So definition of what is a Schur concave. So it's minus Schur convex. So, ah oui, non, c'est Schur SU. Ouais, non. Ouais. Non, mais oui, non, mais je l'ai écrit avec un R dans mes notes, et puis là, au tableau. Enfin, bref. So Schur. No, but because there's a guy in this community who is called Schur CH. So yeah. So I think that's why I messed up. Okay, so what it means to be Schur concave. So as you can see, this value of the entropies, they only depend on the eigenvalues. So I will just give the definition with the eigenvalues. So S is Schur concave. It means that if I look at a sequence of numbers alpha I, so alpha I are it's a sequence of numbers of positive numbers. Yeah, alpha I, in fact, we need two. So two sequences of positive numbers such that for all k, sum from 1 to k of alpha I is larger than sum. So if the partial sums are ordered, then S of alpha 1 alpha k is no, yeah, no. No, that's not okay. No, yeah, no, I shouldn't phrase it like this. Okay, now I realize. Okay, so sorry. So these are the eigenvals of rho B and rho A. Okay. respectively, such that this is true, then yeah, S of rho B is larger than S of rho A. Yes. So this means, so what is kind of the, and so yeah, so this sometimes we say that alpha majorizes beta, okay? So what does it mean? So let's assume that this proposition is true. Then, I mean, a sequence that, so here we say, yeah, maybe I should write it because I will say it. So this means that alpha I majorizes beta. For example, so if I look at these eigenvalues, and I look at the partial sums, this will be by definition larger than any sequence of eigenvalues of any other reduced density matrix because of the trace condition. So where these are eigenvalues of some RBM. Yeah. So I should use maybe like, I don't know, curly. Yes. Yeah. So yeah, I don't know. And this I will write alpha. And so if I just apply the proposition, this means that this S of lambda 1 and so on, this is larger than S of 1, 0, 0, and this is 0. Okay, so by this Shor concavity, you have that this is true. And then this is true. Yeah, okay. So this is true. I mean, just by definition of the Rényi entropies. Okay, so here you would need. So here, for example, you would need rho to be, well, the eigenvalues to be equal either to 1 or 0, and so you can only have 1, 1. So this is automatically satisfied. So you have a condition 0, in fact, by the Shor concavity. So what time is it? 35. Yeah, I guess it's too tempting to do the proof. I will do the proof. I mean, because in fact, it's kind of simple. So I will do the proof in the easy case because the general case, it's. Shall I keep? Yeah, maybe what I can do is like I can keep these there and write the definition of my von Neumann and Rényi entropies. Yes. Where? Yes. So here I have this relationship between these two, smaller than the entropy of a general reduced density matrix, and the entropy of a pure state is 0. No, it's yeah, it would, okay, maybe A. Yeah, but then how? Yeah. Yes. Okay. Yeah, that's true. Yeah. Okay. So. Yeah. Okay. I will change some stuff. I mean, I'm not sure. So rho prime. I will call it lambda I prime. So if lambda, yeah, so if I put a prime here, then the prime goes there. Okay. And so,
you mean S of the row.
With, yes, so it's, yeah, so I is, yeah, I think I will not make the difference. So I will, yeah, I will abuse the notation. In fact, it's related to, well, I mean, for this, I mean, it's just related to the fact that yeah, I mean, it's related to the fact that this is so minus rho log rho. This is concave. So yeah, proof, easy case. So we'll do the case where you have just two eigenvalues. Okay, so you have so you have just lambda 1, lambda 2, and lambda 1 prime and lambda 2 prime. So in this case, this condition, I mean, it becomes so then the condition becomes, even write this, so it's lambda 1 larger than lambda 1 prime and lambda 1 plus lambda 2. So here, since these are the eigenvalues of a reduced density matrix, this is equal to 1, and so it is equal to lambda 1 prime, lambda 2 prime. So now if I put them on an axis, okay, I have lambda 1, which is larger. So lambda 1 prime, let's put it there. These two, they need, yeah, prime. So lambda 1 and lambda 2, they sum to 1. Same thing for lambda 2 prime. So lambda 2 prime is in fact here, and lambda 2 is here. I should have used different colors for the primes. Yeah, let's use different colors. Okay. And so, yeah, the idea is to just see that this one, you can write it as a convex combination of lambda 1 and lambda 2. So lambda 1 prime, it's a convex combination. Yeah, let's write it alpha lambda 1 plus 1 minus alpha lambda 2, where alpha is between 1 and 0. Lambda 2 prime, it will be well, you just switch the coefficient because of the equality. And then, yeah, you just use the concavity, and so now you can use just the concavity of the functions here. So if I plot, for example, this one, so I plot minus rho log rho when rho is a number. So I go from 0 and I go to 0, and it should kind of look like this. Kind of. So it's concave. So now, if you look, so for the von Neumann entropy and for the two, and then you use concavity of the functions, and then you find this. So I'm not, yeah, I think you are more or less convinced.
But this is a unique one eigenvalue which is 1 minus the other. So take the von Neumann entropy is lambda 1, lambda 2. I think it's called the unique entropy to x log x plus 1 minus x log 1.
Oh, yeah. And so, yeah, so if I look at the table, you have, yeah, so these two are satisfied. So this, yeah, this gives you, so yeah, I mean, so this you have for so this is So you have it for von Neumann and Remy, and you have it also. Yeah, I used orange and it's green. So this you have for von Neumann and Remy. This you have for von Neumann and Remy. The additivity, yeah, maybe we can do it in one line. So yeah, the additivity you will have for both. So why you will have for both? So it's because if you look at the so the eigenvalues of row A tensor row B, I mean the eigenvalues of this guy, that will be the product of the eigenvalues of row A and row B. And so then, I mean, you just insert it in the definition, and you see because of the log, I mean, the things will split. And here, because you have a log in front of here, well, the same thing will happen. So you get additivity. So this will be, you will get additivity for von Neumann and Remy. So let's add that. Now let's go to the subadditivity. Subadditivity. So here you have to distinguish the cases. So let's look first at the subadditivity for von Neumann. So the subadditivity for von Neumann, it relies on a nice inequality. So it's true, and it relies on what is called Klein's inequality. So it's an inequality about the trace of matrices. So let's state the inequality. So I have F, which is convex, and I have two matrices, M and N, which are, yeah, let's say symmetric in Hermitian works. And so basically, when F is convex, you have let's draw a convex function. Yeah, let's draw it like this. So if I pick 2 points, X and Y, and I draw this thing here, you know that for every convex function, f of y minus f of x, it's larger than the slope that you have at x. Yeah, let's draw the slope here. So this slope here is f prime of x. So times y minus x. And now you want to generalize this for matrices. So I will write something. So I just substitute y by my matrices. So this is n, m minus n. So this is what I want to write. Of course, it doesn't have any, so it doesn't make any sense. And so to make some sense, I put a trace. And in fact, if I put a trace, then it's a theorem. And the proof is just by doing the eigenvalue decompositions of n and m. You just write the eigenvalue decomposition. You use the convexity for f on scalars, and you find the inequality. So, but it's exactly the same thing. And it takes 4 lines, but yeah, I don't want to do that. So now let's see why it's true when you deal with the von Neumann entropy. Yes, I differentiate f as a scalar function. No. No, I define f as a scalar function. I mean, yeah. I mean, there's no different meaning. Yeah, I just have two matrices, so I don't have any map. Yeah, okay, yeah, in this sense, yes, okay. No. Yes, okay. Yeah, okay, no, but no. So it's yeah, as a scalar function. So okay, so let's see why it's true. So why so now a proof of the subadditivity. For von Neumann. So you write down yeah, maybe I should do it in the other board. So you write down this. What you want to. So you want to show that this is non-negative. So you write the definition. Yeah, I should have written the other term first. Well, that's not so bad. Okay. And so now the thing is, the trick is to write this. So the trick first is to write, is to put everything in the same trace, but you see you have matrices that have different size. So what you do is you write the following. So you make everything the same size. To make everything the same size, you introduce identities. Okay. You do the same thing here. So here, yeah, I mean, this is equal to this because I don't do anything when I look at the entropy of this, of row A times identity. I just yes. I mean, no, because here you see it's so if you look at the eigenvalues of these, they will be so it will be the eigenvalues of
can also see from the two actions.
non mais attends, il n'y a pas un truc. Ah ouais, non mais c'est pour ça. Attends. Ouais, du coup. Ah oui, non mais oui, ça, j'ai pas le droit de le faire par contre. Ok, ouais. Ouais, non, ça, oui, ça marche pas. Attends. Ouais, mais du coup, ça je croyais que c'était l'étape intermédiaire, mais non, ça, c'est pas vrai. Ok. Par contre, un truc qui est vrai, c'est ça. So what is true, it should be this. Because so here, so So to go from here to here, what you say is that the trace, not inside the log, that is important. Because you want to factorize by this thing and then put everything in the same. So here, just use the fact that if you trace, so if you trace over B, row AB, this log, this is row A log row A. And now that I read that, yeah, I'm not sure anymore.
So the log of tensor the identity, tensor of the log of A.
It should be the sum then. It's the sum, so it would be the log of row A tensor identity. Yes. No, because row AB, then it has the same dimension of this. So then this, it should be the sum of the log. And then the log of identity, it's 0. And so now, and so if I trace out, so if I trace out B, I should get that, I believe. So I think it's correct. Yeah, the partial trace on B of this thing gives you that. I think this is correct. I mean, if you are more or less convinced, then I can carry on. And so, yeah, so then you factorize by row AB. And you gather the log, so you use that. So here, then you use. So here in this step, you use that log of M tensor N. It's the log of M tensor N plus the log plus M log N. So so these two, you gather them in a product. And so in the end, what you are down to is to prove, now you prove that the trace M log M minus log N for Hermitian matrices, this is non-negative. And this is a consequence of the Klein's inequality. Yeah, shouldn't erase that. And so this is one further line. So yeah, so you just use Klein's inequality for x log x. So you have the trace of M log M is N log N. So the derivative of x log x. So this is 1 plus log x. So the derivative, then I have identity. So I have a M minus M plus the log of m minus n. What? No. Yeah. No, it's yeah. I differentiate, but evaluate at n. And the thing is, yeah, this is true if the traces are equal. And they are equal because they are reduced density matrices, so their trace is 1. And so, yeah, and so this thing goes away. This trace goes away, and then this n log n cancels with this n log n. And so you have trace of m log m minus m log n, which is non-negative. And so, if you plug that in, it's non-negative. Yeah. So yeah. So for the von Neumann entropy, the subadditivity is true. By similar manipulations, you can show also that the strong subadditivity is true. So this holds for von Neumann for both. But for the Rényi entropy, it's not true. So there are counterexamples. So for Rényi entropy, you don't have subadditivity and you don't have strong subadditivity. So that's for the next thing. Yeah. Yes. Von Neumann is the only one that satisfies everything. Rényi doesn't satisfy these. No, I think it's just no. You can check that it holds true for von Neumann, but yeah. I mean, I guess they are. Well, they could be, but they are not known. Yeah, I guess. So yeah. So if the question is, if you set these conditions, do you have only von Neumann entropy? Yeah, the answer is I don't know. And yeah, the answer is I don't know, but I believe that yeah, that people are trying to find something that because it's yeah. And it's too bad that Rényi entropy doesn't satisfy that. So why yeah? So why people care about Rényi entropies? So it's because so the reduced density matrix encodes the singular values of the reshape of your relevant matrices, and for the tensor train approximation, and well, the entropy kind of encodes the deviation with respect to a pure state. Yeah, and something that I should have mentioned is, yeah, the Schur concavity. Yeah, okay. So it's a remark that I have not made. I should have made earlier. So about the Schur concavity of the entropy. So von Neumann or Rényi. So what it says also is that it will so the entropy will be lower if the profile of these eigenvalues. So here I plot the eigenvalues of rho. So typically it should favor eigen. So if you have a profile like this, so something which decays quite nicely compared to this, then, well, I mean, if if you are in an example where these are close to 1, you can believe that this shape is this shape of the eigenvalues should majorize the one in green. So yeah, I don't know. Let's call it this one lambda and the other one mu. So if lambda so majorizes mu, then by definition, the entropy associated to mu is larger than the entropy associated to lambda. Of course, I mean you cannot. So it's not. How do you call it? It's not a total order. Like you cannot compare any sequence basically. I mean, yeah, it's a partial. Yeah, it's a partial. Yeah, it's a partial order. You cannot compare any sequences. You have to satisfy this condition on the partial sums. So it's quite restrictive. And so yeah, and so what it means is that yeah, it should favor profiles that are steeper with respect to something which has a slower decay. Well, because yeah, but you have a finite number of them, and and the thing is no, and also they sum to the same thing. So you cannot have any kind of okay, they sum to the same thing in the end. So you cannot have. It's not an infinite tail. So because of this condition, I mean, if they are, yeah, if the lambdas they are all in this sector, then you are very close to 1. So with so this sequence would majorize approximately everything. So that's why in this, so that's the interpretation of the measure of the decay of the eigenvalues. But the thing is, so now can you transform this into the following statement? So can you say that if S of rho is small, then the eigenvalues are small. Well, the eigenvalues decay fast. And so this statement then becomes, so if this is true, then it means that the state psi is well approximated by a tensor train of rank R reasonable. And the thing is, so the answer is for the von Neumann entropy, you can find states that have a low entropy, a low von Neumann entropy, but that cannot be approximated well by tensor trains, and vice versa. Like you can have states that have low. No, not vice versa because the example. So so you have kind of a negative result for the von Neumann entropy. So in the asymptotic where the dimension of the system is large. So in the sense that you have then a control, so that if you make the system larger and larger, the entropy doesn't grow. But to make it approximable by a tensor train, you will have to increase the rank with the system size. So then, yeah, for the Neumann entropy, you have so you have examples of S of rho bounded, so uniformly in the system size, but require R that is exponential in L. Okay. For a TT approximation. Yeah, for TT epsilon, yeah, at accuracy epsilon. So you set your accuracy and you show that you cannot achieve that. So it's sad.
Depends only on the shape of your approximation.
No, well, so at first I showed that if you have a state that is a TT, then its entropy is bounded by the log of the ranks. And so this, this property kind of, so what you want to say from this example is that if the entropy is small, then the eigenvalues decay fast. So you should have a good approximability by tensor trains. For the von Neumann entropy, it's false. You can find examples where it's not true. I mean, I'm not saying that it's a generic example, but there are examples that you can construct. And for the Rényi entropy, you have you have a positive result, which states that if the entropy, so if this is, so for alpha, which is less than 1, so if this is bounded, then you have really a TT approximability. So you can find. But for the Rényi, you don't have the subadditivity, you don't have the strong subadditivity. And the thing is, it's not that surprising because here you're really measuring the sum of the eigenvalues to a power alpha, which is smaller than 1. So you are really measuring a decay of the singular value. So that's why it's not that surprising. Yeah, then you would need to control this for all cases. Yes. Example where this is bounded for all cases. Yes. Well, because these are some natural properties that you want to have on the entropy, I think. I guess as chemists, physicists. No, but I think it's they are reasonable properties if you want, I think. Yeah, I think so. Yeah, so I think I went a little bit over time, so let's stop here. Ouais, c'est marrant. Ouais, je sais pas, peut-être c'est un peu fichi ça, ouais, mais j'ai l'impression que c'est bon. Okay, so let's finish. So we have 1 hour about tensors and then it will be over. So 2 topics that I want to finish with. So first, the ordering scheme that is used in DMRG, quantum chemistry DMRG, to have a good guess of the ordering of the orbitals to start the MRG, and then finish with asking the real law. So let's go with the Fiedler order. So the principle of the Fiedler order is, so it relies on the following. So it relies on the measure of, well, on the von Neumann entropy, which is maybe not the right one for the tensor train, well, to characterize the tensor train approximability, but I mean, well, but that's the one you use because you need the subadditivity condition that you don't have, unfortunately. In fact, even this, you need a strong subadditivity condition. So first, I will introduce the mutual information. So what is the mutual information? So it's a matrix. Which looks like this. So you look at the one site and so the sum of the one site entropies minus the two site entropy. And so by the subadditivity, this is a non-negative quantity that we call the mutual information. And so it is 0. Well, yeah, it's something that I haven't said. It is 0 if it's a tensor state. Okay, so if it's in a tensorized state, it's 0. Otherwise, you have a correlation between site K and L. Okay, and so why this quantity is interesting is because if you look at so if you want to kind of characterize the tensor train approximability, you want to bound the block entropy, so the entropy of 1K. So you want to bound the entropy of the whole block. So yeah, usually this quantity, yeah, I'm not sure I've said it before, but it's called the block entropy. So why block? It's because if you write some sites like this, it will be the entropy with rest. Well, it will be this, this block. So that's why they call it block entropy. Yeah, I mean, it's a picture. And so this, by just the subadditivity, it will be smaller than the sum of the one site entropies. Okay. Okay. So this is just by subadditivity. So one thing that people kind of know or kind of do is what they did at the beginning in the MRG is that this is a bound on the block entropy. So what you can try to do is put the states with put the orbitals with the least one site entropies at the edge, so over here and there. So I have I don't know, if I plot the S of rho J, you would like to put them so that it looks like this, kind of, because if you do something which looks like this, I don't know. I'm not sure. Maybe something like this. Then basically you screw the entropy of the whole block. Well, it's an upper bound, but let's say the upper bound is sharp, then you would screw the entropy of all the blocks. Whereas here you just have a large entropy of the blocks in the middle. So the thing is, you can be a bit more. So you can have a sharper bound. So the sharper bound that you can get, for the proposition, the sharper bound that you can get is the following. So I don't think I will prove it because it's it's yeah. I want to speak a bit more about the area law. So it's this thing, J plus 1, yes. And so this I, yeah, yes, sorry. Okay. It's the sum, but until I think, well, it doesn't really matter. So you just miss one. Okay. So it can be a bit sharper. You can bound the block entropy by the sum, the one site entropy minus the mutual information, which is a non-negative quantity. So it's a sharper bound. And so what it tells you is that and that's the idea of the Fiedler order. So what you want to do is so you compute one site and two site entropies. You compute the respective mutual information and for all sites, okay. But the sites you have just so sites you just have the number of bases square, okay. So you have so
How do you do that?
so you compute an approximation of the solution. So for example, with the I don't know, for example, DMRG with the low bound dimension. And what you believe is that since this is related more to the shape of the singular values, you don't need an accurate computation to have a good idea of a good approximation of the entropy. But yeah, so you compute that, so it's an L square matrix. And now, because of this, what you want to do is to find an ordering of the site which maximizes the mutual information of neighboring sites, such that this bound is sharper. So that's the Fiedler order. And so the proof of that is just using the strong subadditivity. So yes, so the Fiedler order is just so it's just find the permutation that maximizes the neighboring mutual information. Okay. So I mean, well, finding a permutation it's hard. So you find a proxy to this problem. So I don't go into details, but yeah, I mean, okay. So the interpretation that I can give, which is quite nice, is that you view this as weights on graphs, and what you want to do is kind of yeah, partitioning of your graph, which is the minimum cut. So it's related to these kind of problems. So, but since the matrix is not that large, I mean, then you don't have to do fancy techniques.
Matrix of the graph, you find the eigenvector.
Yeah, the eigenvector of the Laplacian, and then yeah. So I mean, it's named like this because it's related to the Fiedler vector, which is yeah, for the people who know. Yes. Yeah, this you can compute quite easily because you can because these one site entropies, they are just related. So it's something that I have not really mentioned, but this is just so you just need to compute quantity like that, okay, or like AK dagger. And the thing is, this is an MPO of rank 1, this is an MPS, and so the expectation value is easy to compute. So you have access to these quantities really easily. So you change the, I believe that you change the, you don't change the one side, but you probably change the two sides, yes. If you change the ordering. Yes. So it's, yeah. I crois que oui, je crois que tu changes. Yes, sorry. Yeah. I mean, it's an empirical scheme. But
if you have the exact state, the one which belong outside of depend on the other because just usually consider your formula.
yeah.
Because here in the figure order, you order such as the neighboring ones. That depends on the order, but why? The list of neighbors depends on the order. But
the thing is, I don't know it. No, yeah, okay. No, but yeah, if you have the exact solution, it should be independent. Yeah. Oh, you're right. Yeah. And so, yeah, maybe let's go back just to the example that, I'm not doing the full explanation for, yeah, I printed too many things. So for the example that I have given at the beginning, so in fact you can run the full algorithm, but what is interesting is just so yeah, maybe I should recall my example. So in my example, I had bonding and anti-bonding orbitals. So I had so this was my computational basis. My state psi was a superposition of both. So it was phi b. Yeah. Yeah. Well. Okay. And so you can compute for this state the one side one side reduced density matrix, the corresponding entropy, the two side reduced density matrix, and the mutual information matrix. And so what you realize is that if you look at the mutual information between sites that have different spins, since it's in this tensor form, the mutual information that you find is 0. Okay? Because it's in the tensor form. Now, if you look at the mutual information between, well, phi b up and phi a down, phi a up, this is a positive. And for the mutual information between downsides, this is also positive. So what it tells you is that there is a kind of there's an entanglement. It's between these two orbitals, not electron orbitals, and that you should put the spin up and spin down orbitals together by the previous criterion. And so it's exactly the order that was giving a rank 1 approximation of this tensor. So what this tells you is that you should put phi a up and phi b up together. Okay, and the same thing for phi a down phi b down. And so, yeah, so you had, so for example, phi b up, phi a up. So the ordering, so this ordering is favorable. Yeah, is the result of the Fiedler order. No, I mean, the I are given, then what you want to maximize is the neighboring ones. And so now what I say is that if I label them, so what I could do is label them by 1, 2, 3, 4. But in this case, this mutual information, they will be by a distance 1 apart. Because this will be I1, 3. And I would like to be I1, 2. And so to have it I1, 2, well, I just use this ordering.
Can you explain again why these are 0 and then because you can label these orbitals as by 1 and by 1 up, by 2 down?
So this is 0 because it's a tensor state between up and down orbitals. So if you compute so this is called the relative entropy sometimes, or sometimes the Kullback-Leibler divergence, if you want to be fancy. But yeah, I mean, here it just illustrates the fact that it's a tensor state between up and down spin. Whereas here, well, this illustrates the fact that yeah, they kind of come together. So yeah, so that if you, so they come together. So if you trace out this guy, you see something between this and this. Well,
By 1 up, by 2 down.
no, you would get something different than as mutual informations. No, here I just reorder the things. Same state, but I reorder the orbitals. Yes.
But the definition of the I does not depend on the ordering.
No. The definition of the I. It depends on the state psi, but not on the ordering of these bases. And now, yeah, and I thought it would be, I don't know. No, but I mean, this is my state. I can, so I mean, I can write it in a. So I always use these bases, but yeah, and I can compute the one side reduced density matrix and the two side reduced density matrix. I obtain these results. I mean, it's well because it's a tensor state, tensor between up and down. So it's up times down, yeah. Yes. Okay. So yes.
The position you may actually put the bound on the entropy. It relates on the property and fourth property.
Yes.
So, but you actually need a scheme to calculate the entropy. It's one of those that we see before. So how does it behave if you are using a second scheme that do not compute the fourth property? If your statement is based on, I don't know,
You mean yeah, what do you mean? Like can you use that if I substitute this S by the Rényi entropy? This, I mean, okay, so this is not true because then you don't have the Rényi entropy doesn't satisfy the third and fourth conditions of the subadditivity and strong subadditivity. So there's no reason why it should work.
In which cases would you use that if you compute the entropy?
So the thing is, so if you are given yeah, I mean, it's not entirely true, but yeah, because this should actually you could these quantities you can compute actually when you have something which is given as a tensor train. So I don't really know why they do this, but yeah, it's another question. I guess it's because then it's hard to, I don't know, it's hard to develop a scheme. Yeah, well, yeah, but they could compute it for all the, you know, the. Yeah, that's true. Yeah. So yeah, maybe I was deviating from your question. Yeah, I forgot what you were asking. Okay. Yeah. But yeah, so you are kind of, you know, so yeah, I mean, you are kind of, you know, yeah. So Rényi is good to tell how you can approximate it by well, by your ansatz, but then, yeah, but then the scheme that gives you a way to choose the ordering of the orbitals relies on properties that the Rényi entropy don't have. So.
Is there any way to circumvent that? I don't know, just some intuition that gives you good guess of what a good ordering could be instead of starting it blindly?
I mean, the thing is, if you start blind and you pick, so generically you would pick a wrong ordering if you start. So that's, I mean, because yeah, because good orderings are really, yeah, scarce in a sense, and so, but it's not it's not too bad because in the end, what you are interested in is having access to these quantities that converge fast, because they depend on the high singular values or the high eigenvalues of these matrices. So you don't, yeah. That's yeah. That's my understanding. Yes, I think so, as a, yeah, as a proxy at the beginning, yeah. So yeah, I played around this and I used also some CISD reference also to, yeah. But it's really hard to do something better than this. I mean, I tried, I failed. So yeah, and in practice it works well, and when it doesn't work, then you do some kind of little perturbations of the permutation that you are given by Fiedler, and yeah, hope for the best. Okay, so yeah. So area law. So I believe it's 5. Casting the real law. So the area law, yeah, so it's a rigorous result that tells you that you have ground states of one-dimensional nearest neighbor Hamiltonians that can be approximated can be efficiently approximated by tensor trains. So the setting is the following. So you have an Hamiltonian, which writes as nearest neighbor. So as a nearest neighbor Hamiltonian. So yeah, I mean, if I want to be a bit more precise, so H is acting on the purely H, which is the tensor product of J copies of this. I mean, yeah, this is to be a bit fancy, but think it as R2, okay? All these HJ, so this one would just be R to the 2L. And this AJ, J plus 1, they all act on HJ tensor HJ plus 1 in the sense that that this, in fact, its identity over all the previous Hilbert spaces times something times this. Okay. So it's in this meaning. So when I say that this acts on this, I mean it's kind of an abuse of notation, because this acts really on the full Hilbert space, but it acts as identity on all the other copies of HJ. Okay. Yes, I mean, in terms of creation annihilation operators, this would mean that you are acting on, so if you, yeah, let's pick another letter, T. So it's I plus 1, AI dagger, AI plus 1, plus AI plus 1 dagger, AI. So if it's one body and if it's two body, you just add the relevant two body terms. Yes. The only thing that is required is that the commutator between so the technical assumption is that the commutators, they need to be uniformly bounded, because two neighboring interactions don't commute, and they are all also bounded uniformly. Yeah, and another thing that is important. So now we are looking at the scale where L goes to infinity. So now we are interested in the behavior when L goes to infinity. And so, and we are looking at the ground state of H. So what we are going to assume is that there is a gap in the infinite system. So between the ground state of the infinite system and the so there's a gap between E0 infinity and yeah. So there's a gap. So yeah, maybe let's take the theorem. So the theorem by Hastings, or Hastings, I guess it's. So it's a recent. It's fairly recent. I think it's 2005, maybe 7. The paper is not easy to read, but it's rigorous. I mean, it's not like a. Finish the sentence. There are not too many gaps in the proof. And the theorem states that, so you look at the ground state projection, and what it states is that you can find, so there is So, okay, I will write it this way. So there is a, yeah, I'm not sure these are great notations, but yeah. So there is an operator. So first we need to pick a little l, okay, which is an integer. So there is an operator which is acting. Maybe it's okay. So for all k, which is some index from 1 to l, and for all l, little l, you can find an operator which is acting on the tensor spaces j minus l. No, I call it k, so it's k minus l, k plus l. Okay, so this is just a shorthand notation for this is crumbling. So this is a shorthand notation for this tensor k minus l plus 1, tensor blah, 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 until the last one. So this is acting just on 12 copies of my Hilbert space. So it's M for middle. Then I have a left one, which is acting on H from 1 to K. And then I have a right one, which is acting from K plus 1 to L. And what I can say is that my ground state projection, and they are all bounded by 1, can be written as a product of these three operators plus a correction, which is exponential in the number of sites that you have in your middle operator. So so let's just contemplate that for a moment. And the big O doesn't depend on big L. Yeah, I think it's yes. So what does it mean to have that? So so what does it mean? So it means that if you are looking yeah, so if you are looking at the okay, I will draw pictures. I'm not sure it's the right one, but yeah, let's pick a site K. Okay, and let's say that L is equal to 2. So the support of my OM operator, so yeah, little is equal to 2. So I have the support of my middle operator is just from K minus L to K plus, so K plus 2 and K minus 2. Then yeah, purple. Then the support of my left operator is this one. And then the support for my right operator is this one. Okay. So if I had, so for example, if OM was just the identity, so it wasn't there, what it would say is that psi naught, so the ground state projection, would be a tensor product between the left and the right. So it would be a tensor product of a density matrix that only acts on left and only acts on the right. Okay, so the tensor train representation of my ground state would just be of rank 1. So this is if this guy is identity. Now the thing is, this guy is not identity, but it acts on a little Hilbert space. It acts only on a little Hilbert space, which is of size little l. And so what it means is that the representation of this operator, when you look at the rank here, it will be exponential in the size of this operator. Well, exponential in the size of the support of this operator. So the TT rank at K is so scales as the support of OM, so it scales as a little l. Are you kind of convinced with this statement? You are too tired to. And so, and so, what is interesting is that this is then independent of the size system. Yeah. So this big O is it's uniform in capital in the size of the system, and that so if you want this factorization to be more and more accurate, you just choose the support here to be larger and larger. So in this sense, this is yeah. Yes. They are uniformly bounded, yes. Uniformly bounded, and the commutators are uniformly bounded. You need both. And the little c, yeah, it's related. Well, I will see to what it will be related. So yeah, so where's the area? So why do we call it area? So it's called the area laws. So why is it called the area law? So it's related to the value, so to how the entropy scales with the size of your reduced density matrix. So so let's just so yeah, in the okay. So if I have okay, if I have k sites, so let's pick a random state. Okay, so if I pick a random state and I look at the block entropy with the k sites, then I have entanglement with everything in with every other site in my system. Okay. And so how is it reflected on the entropy? The entropy scales as the number of sites that you have in your system. So for a random state, this thing here scales as the number of sites that you have in your system. So this is exactly the bound that we had when I had all the singular values that were equal. Okay, so it means that you have entanglement with, so all the sites have entanglement with everything. And so the number of sites here, in this case, it will be the volume that is in my system here. And now this result here, it states that basically, if you look at the entanglement here with the rest, the entanglement that I have with the rest of my system here, it's exactly the entanglement that I have for the rest of my system for OM. And this guy has only entanglement with a few sites here. So it doesn't scale as the system size. It just scales as well, it's in fact bounded. Okay. So here in this case, the entanglement is well, the entropy is bounded. The entropy is uniformly bounded. And so this is related to the fact that well, the surface that you have at the interface is just one because it's one-dimensional. And so this is called the area law. So here, the fact that this is bounded, it means that here it's the area is just one. Okay. So for one-dimensional system, it's a bit I don't know, kind of how do you say it? Of little l, yeah. Yes, yes. Yeah, it's a point law in 1D. I mean, yeah, I think the picture is better in 2D. So if in 2D you have kind of something which yeah, let's do another one. So if you are looking at this here, so you would say that the entropy should scale at the number of sites inside, but then the so I mean this is less rigorous, let's say. But there are results that states that the entropy of the ground state of, well, the reduced, yeah, the row of, yeah, let's call it A, this scales as the area of Mayer square. Okay. So people say it's true, but I think it's not. Yeah, there are no. Yeah, because this is really tied to 1D. Yeah, I mean, people claims that it's a theorem, but yeah, I think it's. Yeah, not sure if. Yeah, I haven't read the proof. That's it. Well, yes, I think I have half an hour. Yeah, so that's why it's called the real law. But I think what is, I mean, to me, the interesting bit is this factorization, and the way that the real law is derived is really by using this factorization. I mean, that's what is interesting in the theorem.
The Asting theorem. So in 1D, it's kind of a spatial system, right? And you have the Bethe ansatz for the system that it's an ansatz that is exact of the ground state wave function. So is it? So there is no protection, and you cannot use the Bethe ansatz to show that indeed the wave function can be factorized, right?
Yeah, I mean, every time that I looked at the Bethe ansatz, I was wondering if it's really like some. So I believe that it satisfies some kind of an equation that you need to solve. So it's maybe lower dimensional, but yeah, I mean, okay. But it doesn't rely on this for reasons that I don't know. Yeah.
And another point is that can you extend this result to the continuum case? So you have the Hamiltonian on the real line.
Yes, you can. Yeah. It has been extended to the infinite dimensional setting. Yeah, but with the same sort of assumptions.
So the Bethe ansatz can also be extended.
Yeah. Yeah, I don't know much about Bethe ansatz. Yeah. Yes. Okay, so maybe let's discuss the sketch of the proof. Sketch of the proof. Yeah, I think so Antoine, don't complain too much. I think you won't like it. I know, but I think because I think I don't understand it fully, so that's why. So that's not what you do. No, that's not what you do. So what you do is the following. So I mean, there are two and a half ingredients, let's say. So first ingredient, you have the Lieb-Robinson bound. So the Lieb-Robinson bound. So you pick an operator. Yeah, we use the same words that I've been using. So which has support on Hx. Okay, so think of X as a collection of sites. B, which has support on Hy. And X and Y are disjoint. Union, not intersection. They are disjoint. And you have the Hamiltonian, which is of this type. And you introduce A of t, which is an evolution of your A. So since the H has interactions between X and ultimately Y, this won't have support in the original Hilbert space. It will kind of leak in the other Hilbert space. So now you want to characterize the deviation of the deviation of the commutator between A and some operator that has support only in B. So A of t and B. So this you can bound by some constant that depends on the operator, the norm of A, the norm of B, and also the geometry of the sites of X and Y. So it's not that important, but more importantly, it's exponential. So you have a constant here, well, I called it A, times the distance between X and Y minus V times absolute value of t. So so let's maybe pick an example. So let's say that X is, for example, the first K sites, and Y is, I don't know, the K plus 3 sites and the rest. V is a kind of it's a constant that is positive. Yeah, that is related to the Hamiltonian. So it's a quantity that depends on a Hamiltonian. So V of the Hamiltonian. So it's intrinsic of the Hamiltonian. And so what it states is that you are so if t is very small, then you are almost commuting with all the operators that have support far from X. But as soon as t becomes larger and larger, well, these two minuses, they well, basically you have it's kind of a speed, light speed, wave dispersion. So you have a light cone. Yeah, that's the word that I was looking for. So you have kind of a light cone. Okay. And yeah, the thing is, this dispersion, it's exponential in t and not more. It could be, I don't know, because it's not a wave equation. Yeah. And the proof is not, I mean, it's not nice. I mean, no, but I mean, it's just you do, I don't know, some summations and so on. Yeah, I don't know. I don't find it very, I don't understand what is the gist of the proof. It's just true. So it's this V is it's a kind of a group velocity, if you want. It's how the information. So this would tell you how much the information travels from X to Y, and this is related to the Hamiltonian. Yeah, but I don't know. Yeah. And so the thing is, you use this Lieb-Robinson bound to find an approximation of this guy. So basically, what you say is that yeah, I mean, so what you say is that since this holds for any operator B, which has support here, what you say is that you can find a good approximation of the evolution of A. That's roughly the idea. So you say that so then the corollary is that you can write A of T as some operator A tilde of T, where A tilde has support so where A tilde of T has support on H of X. Okay, so it's a way to truncate your operator just to, and so this, of course, you can just do it for little t's. Okay. So that's the first ingredient. And then the second ingredient, it relies on, the thing that I should have said is that, well, I mean, here you can just shift the Hamiltonian. So you shift the Hamiltonian such that the ground state is 0. So here you say, so I mean, it's more for the proof actually. So here you say that the ground state energy is equal to 0. And so then what you can write is this approximation. T squared over 2q dt. Because so if it has only, so if the ground state is well, because then the other modes, I mean, they are well, because of the assumption on the gap, then the other modes they are slightly away from 0 and positive, and then you have a Fourier transform of a Gaussian. So then the error that you make, so here it's in fact the error that you make is of the order exponential minus the gap square. Yeah, I think something like that. So yeah, Q. So you have a parameter Q, yeah, something that I should say. So you have a parameter Q that you need to choose. But yeah, basically you have something like this. Yeah, gamma square, yeah. So yeah, it's yeah, I mean, it's how, yeah. And yeah, and so this splitting over here, it reflects the fact that you can do the splitting at the level of the Hamiltonian. So I will erase here. The splitting that you have here is the splitting of the Hamiltonian. So now, yeah, so now basically the idea is to try to work on that. So you write H as a sum of something which sits in the middle, so which acts on yeah. So this one will act on the same sites. Well, I mean, it's a sketch, so yeah. And I don't have to be so precise. So this act on H. I mean, yeah. I mean, and just give the expression in fact. So you split in 2 parts. So for J from K minus L to K plus L minus 1, for example, plus the rest. So here, because so this one will just act in the middle. And here it will act on the left and on the right. So I plug that in my exponential. And the thing is, I add this term and I introduce its inverse. And yeah, that's where I'm not super happy, but this thing here, this operator that you have here, it's the solution of an evolution equation. Well, an operator evolution equation that I will write. So it's the solution to this equation. Yeah, no, okay, there's no minus here. Yeah, okay, I'm erasing there. And with the initial condition, U0 being equal to 0. So identity, yeah. Yes. Okay. I mean, well, it's kind of the first time that I saw that. Yeah, I guess it's kind of a Dyson equation. And so here you have yeah, the thing that I erased here. So like you have your A of, so you want to do your so yeah, so here the goal is to say that this is in fact something which just acts on M, but you cannot really do that because here these two, they don't commute. So since they don't commute, you cannot just say this one, so I write this as the product of the exponential, I cancel this term, I just get HM. So this you cannot do. So you want to kind of have that anyway. And so the way to have that is to, yeah, have something which looks like this that appears somewhere, and this somewhere is here. And so now the sketch, well, the proof is by saying that this thing here you can approximate by yeah, oh, I don't know, yeah, let's call it yeah, by a m tilde, which acts on yeah, which acts just on HM. So where HM would be the support of so with support purely HM. And so if this is true, then, well, the evolution, well, the solution will have only, well, can be approximated by something which has only support in this thing. And so in the end, the exponential AHT, this is something which looks like this. Yeah. And so here you can really split between something which, because the left and the right, they are sufficiently far apart, so they really commute. And so you have kind of this splitting that appears. So if you would then plug that here, you have that. You have something like this that appears. Plus big O of small. And well, then then it's unfortunately not sufficient, because then if you, I don't know, if you average something which acts on things that I don't know, well, then you need to find a way to kind of do the integral and have operators that don't depend on time. So that's also a tricky bit that that I won't explain. But yeah, basically, then you work hard just to make this thing that depends on time to something which is independent of time. And that's the idea of the proof. Okay. So yeah, so I think that's it for me on the real and yeah, on the Tensor. Ah, there's a question by Hassan. Yes. No, I think because then it really relies on, because this you can use it anyway, and then you just need a Lieb-Robinson bound, and you have Lieb-Robinson bounds for interactions that decay fast enough. I don't think so. Yeah, I think. I don't know. There's a lot of screening that is happening. I don't know. Yeah. Yeah, it's hard. It's you have Lieb-Robinson, and yeah, I mean, to be fair. No, it's not only for 1D. Well, as far, I think you have it for, yeah, for higher dimensions. So that's why I don't understand why people say it's not rigorous. So for example, we had a talk last year by, I don't remember the name of the guy. I think he's in Quantique in the École des Mines. He said that it's kind of a folklore result for higher dimensional spin systems, but to me, it looks like it should be, well, it should go through. So, yeah. So yeah, I don't know. Yeah, I think it goes through, to be fair. Or maybe there's something a bit strange about these Lieb-Robinson bound in higher dimensions, but yeah, basically it depends on the geometry of your sites. So yeah.
For instance, if you want to prove decay of the density matrix, what you do is you have a time binding discrete model, is you can just do a polynomial approximation.
Ah, yeah, okay. Now, yeah. There are similar proofs using that, in fact, and they call it approximate ground state projections. And it relies on the polynomial approximations of. Yeah. But there are alternate, yeah. But there are alternate proofs using polynomial approximations now that, yeah, it's new then. Yes. Yeah, I guess you could, if, yeah, you would just need to find, yeah, maybe what you could do is maybe some kind of a block thing. Well, you can say that you can approximate the lower energy states by using some kind of a formula which looks like this. Because then in the end, the splitting really comes from the operator and these bounds. So it's really tied to the Hamiltonian and not really to the state that you are looking at. Yeah. Yeah, I think so. Yeah. Then you, yeah. Yep.
More question for what is the current of the amount? What kind of systems for?
Yeah, I mean, so I don't know about yeah, what it is doing. So what other methods are tackling, but I think so I think there was a benchmark paper last year about chromium-2, the dissociation curve of chromium-2. Yes. So they are doing fancy techniques on top of the MRG, but what they say is that they claim that they have the best curve, the best dissociation curve of chromium-2.
They use the MRG as the KCCF solver.
Yes. Yes.
But I don't think that, I mean, are there some EC2 on top of the LRD?
Yes.
Yes. Would like to make EC2 as
Yeah.
Station flavor of it.
Ah,
So this is some white wine,
oh yeah.
and this is chocolate for you. Thank you very much for your enlightening lecture.
Thanks.
So, you know, the Judah is very